Hi there and welcome from Ventura, California to today's webinar, UAS Mapping and Survey, Direct Georeferencing and LIDAR, sponsored by Applanix, InsideGNSS, and Inside Unmanned Systems, and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be hearing from our panel of thought leaders, as today's webinar is about hearing from these experts as they address the state of the art and science in direct georeferencing and LIDAR. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during our Ask the Expert panel session with all of our panelists. Now, we've invited you, along with over 600 professionals spanning 58 countries, representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident you'll find today's webinar of value. Richard Fisher, publisher at InsideGNSS and Inside Unmanned Systems, would like to take a moment to welcome you and introduce our sponsor and main moderator for today's webinar. So I'm going to pass it over to you, Richard.
Thanks, Lori. On behalf of the InsideGNSS and Inside Unmanned Systems team, including Glenn Gibbons, Stan Goff, and myself, I extend a warm welcome to our international audience for today's web seminar. We're delighted you could all join us. Our panel of experts today will provide an introduction and brief history of UAS-based LIDAR systems, followed by presentations of real-world applications. In a short time, they'll take us from the theoretical to the very practical. And now, I'd like to introduce our sponsor, Joe Hutton of Applanix. Joe?
Thank you, Richard. Welcome, everyone. Trimble Applanix is a wholly owned subsidiary of Trimble Navigation Limited, and our focus is on providing enhanced productivity solutions using GNSS and inertial technology for various applications, including airborne mapping, seafloor mapping, mobile mapping, and autonomy. In the mid-1990s, Applanix pioneered the use of GNSS-aided inertial systems to directly georeference airborne mapping sensors on manned platforms, first with analog film cameras and then with all digital sensors, including camera, synthetic aperture, and LIDAR. With the explosive growth of unmanned aerial systems for mapping, we now offer direct georeferencing solutions tailored specifically to meet the cost, performance, size, weight, and power demanded by these platforms. The Applanix products and solutions for direct georeferencing on unmanned aerial systems are sold as part of the Trimble portfolio of OEM products for precision mapping for UAVs. Trimble offers a complete range of OEM solutions to the UAV industry that encompass navigation, guidance, control, precision landing, mapping, and surveying. These products range from small, high-performance L1 RTK GNSS OEM boards to multi-frequency, high-accuracy RTK boards and full GNSS-aided inertial solutions for direct georeferencing, complete with post-processing software. We are very pleased to sponsor today's webinar focused on direct georeferencing and LIDAR for unmanned aerial systems. While somewhat controversial, we believe that LIDAR integrated with cameras and direct georeferencing represents the pinnacle of accuracy and productivity, and it will soon become the standard payload for mapping and surveying with UAVs. To further this discussion, we have assembled a panel of industry experts to share their thoughts and experiences on this topic. Thank you for spending the time to join us today, and I hope you find this session very informative. Back to you, Richard.
Thanks so much, Joe. Now, I'd like to turn today's webinar over to our moderator, General Jim Poss. General Poss is the Chief Executive Officer of ISR Ideas, an intelligence, unmanned aerial systems, and cyber warfare consulting firm. He is the founder and former executive director of the Alliance for System Safety of UAS through Research Excellence, the FAA Center of Excellence for Unmanned Research. He's a 30-year U.S. Air Force veteran with combat experience in 4 wars and was the Air Force's senior career intelligence officer at his transition from active service in March 2013. He is a leading expert on UAS, having helped design the U.S. Air Force's remote split operation systems for UAS control and the distributed common ground station for UAS intelligence analysis. General Poss also has extensive experience in cyber operations from his assignments with the National Security Agency and as the Air Force lead for the stand-up of U.S. Cyber Command. He is the 2012 winner of Aviation Week's Curtis Sword Award for his leadership in Anglo-American aerospace relations. I want to thank General Poss for joining us again for today's event. General Poss?
Well, thank you very much, Richard. I appreciate that very, very kind introduction there. So, LIDAR, one of my favorite subjects and one of my favorite sensors. It's something that I think has got a chance to really revolutionize certainly a lot of what we're doing for mapping in the military. It's got the potential to revolutionize our ability to see through foliage. But I got to tell you, I get a lot of doubt from my fellow airmen on LIDAR. For some reason, the Air Force isn't overly interested in it. I don't know why. I think a lot of that's got to do with whether it's a National Air Force mission. And I'm going to say right out front, I'm not sure if LIDAR is ready for small UAS or not. And I'm going to ask the panelists to try and talk me out of that position, because I know that you guys have quite a bit of experience with LIDAR in small UAS. Okay. All right. So next, Lori, I think we've got a poll up next, right?
We sure do. And folks, coming up on your screen is that first poll. And if you would go ahead and weigh in. We'd like to hear from you on the question, can you really use LIDAR in small UAVs? Options here are no, the tech isn't there yet. Yes, but there are a lot of problems in application. Or are you crazy? Of course you can. Okay, looking like 9% of you saying nope, tech isn't there yet. Majority 54% saying yes, but there are some problems in application. And then 38, are you crazy? Of course you can. General Paz, what are you thinking about those results?
Yeah, all right. It looks like, I'm guessing most folks are kind of agreeing with me that maybe this isn't quite ready yet. I know that the 9% there look like they're agreeing that, really there isn't anything going on with LIDAR yet. It's not that I'm not a LIDAR fan. It's great. I'm just not sure if it's ready for small UAS. But doesn't look like everybody agrees with me on that, so that's pretty interesting. Okay, well, I guess with that, I'm going to convince you that LIDAR is a good thing, and we're going to talk through at least some of the problems from my perspective that I experienced when we first brought on LIDAR systems in the United States Air Force. And of course, you've got to ask the major question on this: really, should have Dr. Evil asked for frickin' laser beams on drones instead of sharks? And I got to tell you, I must have gone through 24 briefings from the National Geospatial Agency on LIDAR, and the lead briefer was the biggest Dr. Evil fan. If you can imagine going through 2 briefings with laser every time he mentioned LIDAR, yeah, it gets, even Dr. Evil gets a little older sometimes. But why is the DoD, particularly the Air Force, so interested in LIDAR? And I'm going to make an argument that it's all about the Z. You know, when you're talking about geometry, you got your X coordinate and your Y coordinate, or your lat longs when you're talking about mapping. And then you got that mysterious Z coordinate for altitude or elevation when you're talking about mapping. And the reason that we're so interested in the Z has got a lot to do with our commitment to literally digitize the globe in preparation for the modern cruise missiles that we developed in the 1970s. We came up with the idea that we were going to have intercontinental ballistic missiles, submarine launched ballistic missiles, bombers with gravity bombs. And in the 70s, we convinced ourselves that we could invent this cruise missile that would fly for thousands of miles with a nuclear conventional warhead and strike its target very precisely. 2 problems with that. One, how do you navigate, which the Air Force solved by inventing the global positioning system. Thank you very much, Air Force. And then equally tough problem was once you know where you are, what's underneath you. And the really tough problem we had was most of our mapping at the time was really done to just 2D coordinates. We spent a lot of time, figuring out what the lat longs were, but the altitude wasn't nearly accurate enough, particularly for the cruise missile, because it was going to have to use what we call terrain comparison and figure out what the terrain looked like so that it could get through, even though people were jamming GPS. So how do you turn 2D imagery into 3D? Well, we tried stereo electro-optical imagery. That's where you take 2 pictures very close to each other and then slightly offset them to get that 3D effect like you see in the movies. Another way was to use synthetic aperture radar, which was what we did for most of it, and that's turning the radar from a sensor that's just good enough to pick up aircraft into one that's almost gives you photorealism. But there's problems with both of those. As you can see from the side, you get a bunch of airmen there at our Sentinel-1 station at Langley who are practicing point dropping. It takes a lot of practice to do that stereo imagery. You got to get double the coverage of the target because you need 2 images. It's difficult to process. And you look like a nerd while you're doing it. Those guys are wearing 3D glasses that are sort of like the ones you wear at movies there. Radar is a lot easier to process, a lot easier to get the Z coordinate, but it's not going to deliver the degree of accuracy as a stereo EO is. It's good enough to give you what we call digital terrain models, which is, good enough for cruise missiles and laser guided munitions, but not really good enough to drop GPS guided munitions on. So from the end of the Vietnam War up until early 2000s, nearly all of the precision weapons the Air Force drops were laser guided. And really you just need XY coordinates so the pilot can find the target, put his targeting pod on there, then he paints the target with a laser, and the laser pretty much compensates for the altitude. The bomb's just going to fall down to wherever the laser's at. Enter GPS guided munitions, and that's a B-1 dropping a full load of 500-pound bombs, and that's how many 500-pound GPS guided munitions the B-1 can drop. Problem with GPS guided munitions is you drop them all at once and they will fly to exactly that point in 3D space that you tell them to. So if you're off by the Z coordinate, by the altitude, that bomb is going to drop hundreds of feet short or long depending on how often you're off. So the Z became very important for us. LIDAR advantages that we got was it easily solved the digital elevation problem. Before we had LIDAR, the accuracy was about 3 foot or so. Accuracy with LIDAR can be as good as 3 centimeters. Much easier to process than other types of terrain models. You can just take a LIDAR picture and skin it with electro-optical. And as you can see on the side there, you've got your digital surface model, which is what you used to get from synthetic aperture radar and stereo electro-optical. On the right is the regular digital terrain model, which it doesn't have much detail at all. And on the bottom is a LIDAR picture, looks like of Manhattan, that's partially skinned and partially unskinned. That's the level and detail you got. But there's disadvantages. Weather can impact collection, ground fog, a lot of moisture in the air. Takes a tremendous amount of storage in order to store it. But the big disadvantage, and I'm hoping these guys are going to talk me out of this, is I just don't think we've got a miniaturized solution that'll fit on a Part 107 drone for the FAA. In other words, something that will fit within the size, weight, and power restrictions of a less than 55-pound drone. And even if you could fit it in there, how much data are you going to get flying at 400 feet at 100 miles an hour within visual line of the side of the pilot? Up there on the upper right-hand corner is a NASA WB-57. It's a formerly a British Canberra bomber. That's literally what we put the first LIDAR on there because it was the only aircraft that had the payload capacity to fly that at above 60,000 feet. Now we've got smaller versions that are flying in lighter aircraft like that, but boy, I tell you, that lower right-hand corner is a picture of an Aerosonde. That is a 54-pound UAS. I'm just not sure that you could fit a system that's going to really help into a UAS that small. But I could be wrong, and I'll be the first one to admit it. All right, so that concludes my portion, and let me introduce our next speaker, Louis Graham. Louis is the President and Chief Technical Officer of GeoQ Group, a group of companies whose foci are LIDAR tools and consulting, sensor processing, workflow management, point cloud exploitation, and small UAS mapping systems. So over to you, Louis. Tell us some more details about how LIDAR actually works.
All right. Thank you, General Poss. So I get the privilege of being able to address you on an overview of LIDAR, a little bit of structure from motion, and then my thoughts on where we're going in the future, which is anybody's guess, but I'll give you my opinion on it. LIDAR is actually a very simple technology. So fortunately, the speed of light in a vacuum is a constant regardless of the speed of the emitting platform. That's really an amazing fact, and we take advantage of that in LIDAR. So we just send out a pulse of LIDAR, we wait for it to come back to the sensor, and we measure the time that it took. Now light travels about 30 centimeters in 1 nanosecond, 10 to the 9th second. So it's really all about excellent timing. How good of a clock do we have in the system to do this timing? A single pulse is interesting, and we could do profiling with that, but to really get a nice footprint on the ground over an area that we're interested in mapping or finding elevation model for, we need to sweep the beam around, and we can do that with a moving mirror or with a moving prism. I'm often asked the question, why laser? Why can't we just use ordinary light? Laser really has two principles which are really advantageous for measurements. The first is spatial coherency. So we have low beam divergence, meaning it spreads out at a very gradual rate as we increase the distance from the sensor. So we today routinely fly LIDARs at, say, 20,000 feet imaging the ground and get valid returns from that. And the second good property of lasers is that they're temporally coherent. That means that we can send out a very short pulse and keep that pulse together. All modern LIDAR systems collect energy over time as that energy is returned to the sensor. So at the bottom of this picture, you can see a histogram where we're measuring the energy return with respect to time. So the horizontal axis is time. And where we have a large amount of energy being returned, we say, this energy must be reflecting from something out in object space. Now we can either determine that something or these pulses within the hardware platform, or we can do it in software. We can pass the entire waveform over to software and do a post-acquisition analysis. And these sensors are typically called full waveform devices. Well, we've got this laser, we shoot it down to the ground, we get energy back, we histogram it, we can see pulses, and all that's very interesting. But if we do not know which way the system is pointing, we've got a problem. And so this is where Planix comes in. We need a very precise position system, that is X, Y, and Z, where are we located, and we also need to know in great detail the orientation of the system, or high accuracy and resolution, pitch, yaw, and roll. And we do this with systems that combine GNSS with inertial measurement units, and typically that combination is called a position and orientation system. And here I've got a picture in the lower right of an Planix system used for this type of application. We also need to know where that mirror or that revolving prism is located, and so we have an encoder on the mirror or prism. We show a mirror in this particular illustration that also tells us where that is. So we have to combine an awful lot of information, position, orientation, mirror angle, etc., for a laser beam sweeping the ground. And when we resolve all of those components, we can map the object space that we're imaging, say the terrain, at very high levels of accuracy. So at pretty high altitudes, 15 centimeters of vertical accuracy is, that's an old spec. Actually, the new USGS spec for vertical accuracy is better than 10 centimeters on what we call QL2 data. So this is quite remarkable accuracy that we're getting from a moving platform. As you saw in General Paas's image, we really get these very realistic images that are returned by this system. So if we look at this, which is just an intensity image, we can see where we get the imaging part of LIDAR. Here we have a grayscale image of an area that's been recorded on the ground, and we could use this type of image for planimetric mapping. We can easily trace out roads and other features in this type of reflected image. We usually do a lot more processing on LIDAR data, for example, classification. This is not classification in the DoD sense, but classification in the sense of categorizing points into the object space that they represent. So here I've got buildings in red, I've got vegetation in green, I've got the ever important ground surface, which is used for floodplain modeling and so forth, in orange, and you can see a little bit of water in the right-hand side here. Modern LIDAR systems, as we saw earlier, have the ability to record the energy that's returned from a pulse with respect to time, so that if we have closely spaced objects, as you see the branches on this tree, for example, we can get a bit of return energy from the top of the tree, a bit more from this bush underneath the tree, and then finally some more energy from the ground. And these multiple returns are often called echoes, or simply discrete returns from the LIDAR system. And these are invaluable for recognizing what it is that we're seeing in object space. Am I seeing a visually opaque particle in object space? Am I seeing something that is transparent, etc.? Trees versus buildings and so forth. So here I've taken some data from a mapping mission in Bushnell County, Florida. And you can clearly see the vegetation or trees, and you can see the ground in the lower part of the image. And I've color-coded these points by the echo. So the cyan points were first returns, some of the magenta points and yellow points on the ground are later returns. Here I've filtered out and said, hey, just show me the returns that represent one of many. So there were other returns, but I only want to look at the first one, and that's obviously vegetation. So here we have a really simple algorithm that says, show me the points that reflected from vegetation. Now to address General Paz's question about can I put these on a drone, well, I think that perhaps 3 years ago it would have been very difficult. Today it's quite easy. Here I've illustrated a small LIDAR system from Regal. It's a 5-return system, 250 meter range, with a mass of only 1.55 kilograms. I would say that this represents truly the state of art in LIDAR systems that you could put on a drone today. Now I've got to know where that system is pointing. I have to know the orientation of the drone on which it is mounted. So on the upper right, I've illustrated an Planix APX-15, which is a position and orientation system for drone applications. You could use it in other applications, of course, but it was really purpose-built for drones. And here you see it has a mass of only 60 grams. And below these two, I have a picture of a common drone that's used in mapping today, which is the DJI M600. There's a new one called the M200 that's quite similar. This drone has a payload capacity of 6 kilograms. That means besides itself and its batteries, it can lift 6 kilograms. So you can see that I can easily lift this Regal LIDAR system as well as the Planix PAWS and have plenty of extra capacity to add in an electro-optical camera. So yes, it's quite possible today to do this. All right, let's move on from that introduction of LIDAR to a really competing technology in drone space, which is to take images from different perspectives. This is quite like the stereo imagery that General Paz referred to. If I take pictures from more than 2 locations, I do what is called multi-ray photogrammetry, and through an algorithm called structure from motion, I can determine the location that the camera was when it took each one of these photographs, and this process is completely automated, gives us pretty good results. So here I have a picture that, or an area that we flew of a mine site, or actually this is a paper mill, and you see a wood chip pile that's used as feeder stock to their process, and their application was volumetric analysis. So I think you can see from these images, I have a map view in the upper left, a 3D view in the upper right, and in the lower section of this image, I've cut a profile, which is this white line that you see through the main image, and you can see quite remarkable definition. Looks perfect. Why do I need LIDAR? Well, all is not good with structure from motion. The first thing is that you have to be able to see the object space from multiple camera positions. So if I have heavy vegetation, I can't see the ground from multiple camera positions. And when I do structure from motion over an area such as the forest that I'm showing here, you can see that I'm just catching the canopy. And you can do some further analysis and find out that not only am I only seeing the canopy, but that canopy isn't even at the right elevation because of some correlator errors that occur. So there's a bad thing about it. Can't use it for vegetation. A second thing is that you can get a lot of occlusions when you have to have multiple perspectives looking at object space. So here I've got an example of an image in an urban area where I'm trying to look down between houses. And you can see that I have a lot of voids. I have some trees that are causing that canopy problem we mentioned earlier. And what I've done is I've color-coded this inset image in magenta in all of the areas where I have voids, that is, where I have no 3D elevation. So this technique would not be very useful for urban areas. A third thing I'd like to mention that I don't have an image of here is that you also cannot detect wires with structures from motion. So if you're going to do transmission line modeling, forget it, you're going to have LIDAR. You won't be able to use structure from motion. So really great for bare earth, mine site applications and those sorts of things. Can't be beat, but if you have situations like I've illustrated here, LIDAR is going to definitely be the better choice. Here's an example that we ran into on one of our mine sites where we were imaging a mine site with a stockpile covered in vegetation. The magenta points are where we did survey with a GPS rover. what you might call pogo surveying. And in the lower view, you see where the actual elevation is with these magenta points, but what the structure from motion gave us in the model. So again, just an illustration of the limitation of this type of technology. Great technology, but you have to use it in the right place. Let's move on and look at the future a little bit and what we see coming down the pike in terms of LIDAR. In the left-hand side is illustrated a scanning LIDAR, and that's the technology that I talked about at the beginning of this talk on LIDAR, where we're just scanning and we're picking up individual points. We do a very high rate. We might do 500,000 points per second, for example, but nevertheless, I'm imaging single points. A new technique is to use a flash LIDAR. That is a LIDAR that is not so coherent, or not so divergent. I let it diverge a bit. I illuminate a larger spot, and now I collect the reflection on an array, very much like a CCD camera, for example. So I have a sensor with multiple sensing elements on it and a single laser. And these are called focal plane array laser systems. Let's back off a little bit and talk about detecting light in low light conditions. So there's a real desire in the LIDAR world to be able to fly at higher and higher altitudes, and that means I have less and less energy coming back. So I need a technique by which I can discriminate and find that energy. And so the idea there is to do something called an avalanche. I have a single event that comes in, say a photon comes in and ionizes an electron. That electron ionizes other electrons, and there's an amplification that occurs in this avalanche type event. I could do that in solid state through a device called an avalanche photodetector. I can run that detector in different modes that run from an ordinary photodiode to linear mode avalanche photodetector. So this would be where I really want to see the intensity that's coming back, not quite as sensitive, or I can run it in this avalanche mode and it will just trip over. And as I get single photons in, I get a nice pulse of energy that says, I don't know the brightness of the ground, but I know it's there, or whatever object it is I happen to image. So if we look at the summary of all of this, what do we have? Well, the big advantage of LIDAR is only a single ray is required for modeling in 3D object space. This is a huge advantage over photogrammetry and really the driver behind the invention of LIDAR. Modern LIDAR scanning systems they're proven. So manned aircraft systems, very high resolution, precision, and accuracy. The largest contributor today to high accuracy is a very high quality position and orientation system. So this is where a Planix comes in, and the reason why you must have that technology to be successful. Miniaturization is well on the way, and we can put these devices on drones. Coming down the pipe, Geiger mode sensors, although we still have a big noise problem to deal with. And frankly, I believe the focal plane array LIDARs, probably 5 years out, huge driver for them, because this is the technology that will be used in self-driving automobiles for navigation. All right, thank you, and back to you, General Poss.
All right, well, thank you very much, Lewis. Okay, I'll admit you may have proved that you can mount these sensors on UAS. I remain to be convinced that the flight mode that the FAA is allowing us to fly UAS is going to yield a lot of coverage. I think it's too low, and it's not going to allow you to get the coverage, but maybe we can talk about that later. So, all right, so we're going to go to our first panel of questions, and I really appreciate the audience laying in some really good questions, and I can see them as you type in, and I'll just ask them out verbally because you guys can't see what other folks are asking. Okay, well, first on, Lewis, you did such a great job of explaining what you can do with LIDAR. You said some very interesting things in there when you were talking about the different types of technology, and you mentioned, for example, that electro-optical really wasn't good at horizontal obstructions like power lines and stuff like that. Our pet peeve in the Air Force is it's also not electro-optical is not very good at determining altitude for vertical obstructions like cell phone towers. I mean, could you kind of explain the advantages that LIDAR has in detecting very small objects like power lines or very tall objects like cell phones? Cell phone towers.
Yes, well, as I mentioned before, if I sit down with an operator in the loop and I use very high-grade stereo imagery, I can pick out by hand small features. So stereo photogrammetry is quite good, but it's quite laborious. So I want to use an automated technique, which takes me into structure from motion. Unfortunately, it does not do well in long, linear, narrow features. So cell phone towers are structural pieces of towers. We see it in mine conveyors as well, wires, etc. So electro-optical and automated extraction, not so good for that. Synthetic aperture radar is great, but I get sort of blobs back. I don't get the fine detail that I need if I'm going to do something like tower inspection. So LIDAR works quite well for this sort of thing, where I can let the beam diverge a little bit, and especially if I'm close into the system, I can get down to actually hundreds of points per meter and get a very fine detailed 3D model of the system. It's also quite fast. For example, if I were going to image a cell phone tower with a drone, I could fly probably 4 patterns at about 2 vertical meters per second, so I can cover quite a bit of ground in a short period of time.
Okay, wow, that's great. You know, the next one, and we've gotten 3 folks that have asked us about this, and Jim, I'm going to ask you, if you don't, I know you haven't spoken yet, if you wouldn't mind taking the lead on this. Could you give us some idea of the costs involved here? If I wanted to go out and start my own LIDAR survey company with a small UAS, am I going to spend $10,000, $2 million, or somewhere in between?
Thank you, General. Well, if I'm the Air Force, I can spend $1 million and get one heck of a great system. Or if I'm the neighbor kid next door, I can spend a couple $100 and get a drone to put in the air, and it's a little bit of fun, but it's not real practical. For a land surveying company, they are going to have to make decisions with regard to the amount of precision that they're looking for, what the projects call for. And so from a hardware practical standpoint, the entrance cost for the technology would run somewhere between $25,000 at the low end and $100,000 at the high end.
Okay, well, that sounds good. So it sounds like there's something for just about every price range. Lewis, I'm going to bug you again on this one, and again, we've got a couple questions on that. I kind of alluded to it. Could you explain the impact of atmosphere on LIDAR? I mean, is it really true that if you get a lot of rain or fog or ground points, is it really going to mess up LIDAR?
Yes, unfortunately it will. If I have a lot of moisture in the atmosphere, I can get atmospheric reflections. There's been a lot of work done by I would say the higher end manufacturers, particularly Regal, in alleviating a lot of these problems so that they can be used in atmospheric conditions today that really wouldn't have been possible at all 3 or 4 years ago. Fog remains a problem. Sometimes we're in very dusty environments such as mine sites, and you can run into that as a problem as well. So yes, generally particulate matter in the atmosphere can cause a problem.
Okay, great. And we got time for one last question. And Pierre, you haven't spoken yet, and I know you're an expert on this topic. I've got some folks that are asking, how possible is it to process this in real time? I mean, once you've taken a LIDAR pass, is it automatically available in the ground station within seconds, or does it take hours, or what's the processing time?
Hi, General. Yeah, that's actually one of the main development that's just been happening on the software side. We've developed a ground live station that actually stream data live from the LIDAR itself. So you're able to actually capture IMU data and GPS data straight on your PC computer on the pilot side. So it is actually possible to get a georeference point cloud real-time displayed on your screen. So that helps a lot in terms of operation and in terms of pilot control, basically.
All right, that's great. So that sounds like it's pretty daggone fast. All right, unfortunately, that's all the time we have for questions right now. So, Lori, I think we've got another poll to go through, do we?
Yes, we do. And folks, coming up on your screen is that poll. We'd like to hear from all of you. What is your favorite, what's your favorite LIDAR platform? So you can see the choices there. Large manned aircraft. Perhaps you need the size, weight, and power swap and coverage. Small UAS. You'll deal with the smaller swap, less coverage for greater detail for lower cost. ground vehicle. I don't need the overhead coverage. I'm just street mapping. Or backpack. I need to go inside buildings. Looks like 25% saying large manned aircraft, 53% saying small UAS, 18% ground vehicle, and 4% weighing in with backpack. General Poss, any thoughts there?
Yeah, I am way losing this argument so far. That's a lot of people that want to put this on small UAS. It's looking like, I don't want to admit defeat just yet, but it's looking like I could be mistaken. So that's great. I'll be honest with you, I would have thought that large manned aircraft and ground vehicle would have been the two largest. So that's actually pretty daggum interesting. All right. Well, thank you very much for that, Laurie. Okay, and next up we've got Jim Van Rens, who's the CEO of Rigel USA, the North American distributor of Rigel laser measurement systems. Rigel is the performance leader in the LIDAR mobile mapping, unmanned, hydrographic, and terrestrial-based industries. Mr. Van Rens is an industry leader in 3D mapping techniques. He lectures extensively to professionals and lay audiences alike. So over to you, Jim.
Thank you, General. So good morning, everybody, or good afternoon, whatever your time zone is out of the audience. We can't see you, but we're thrilled you're with us today. There's a couple things I want to talk about from big data to information. The General laid out some challenges, and one of those challenges is the big data nature of LIDAR. So we want to talk to that. And also we specifically want to address high precision Rigel Waveform LIDAR and GNSS integration. So Rigel and Applanix have partnered, and as Lewis told us, GNSS is the enabling technology for kinematic LIDAR. So we're grateful for that. But for today's high precision LIDAR to work effectively from both data acquisition all the way to automated and semi-automated feature extraction, the integration between the GNSS and the LIDAR is critical to its success. A quick word about high precision. In GPS denied areas, we have developed a tool to correct the GNSS trajectories. Simultaneous localization and mapping, typically known as SLAM. This is similar to that. SLAM was popularized by DARPA. It's used extensively on self-driving vehicles, robots, robot vacuum cleaners, etc. But what we're doing is trajectory improvement for higher accuracies and coherent data sets, which we're going to cover in detail a little bit later, and tightly coupled integration of the GNSS and LIDAR is critical. Sometimes LIDAR and photogrammetry are posed as competing technologies. Rigel believes that it's a multi-sensor world. Each technology has attributes that contribute to the overall quest for information, and tightly coupled integration supports that quite effectively. So in the background, you'll see the variety of Rigel products that are all LIDAR engines. And in the foreground are some of the core technologies of Rigel. Today I want to discuss the role of GNSS Applanix systems in the optimum distribution of measurements, and then next, the seamless integration and calibration. So our end users demand the highest possible accuracy and the best possible point distribution. They need clear and distinguishable surface elements for identification. We call that typically calibrated amplitude and calibrated reflectance, but these are all the attributes that are needed for a high precision data set so that we can search out and find commercial markets that work out very effectively with LIDAR. So, as the General indicated, the airborne mapping systems are the standard, so to speak. That's where things began. And here's an example of an airborne system. And what you're seeing here, you're seeing a little target area on the road, target area in the ditch, and of course the laser beams penetrating the cornfield there. That's the nature of a waveform system. It has that ability and a performance to be able to map through that, and this will set the stage then for precision discussion with regards to other platforms. So in this example, as you can read, overall absolute accuracy is around about 2.5 centimeters, which is quite nice. So a number of different LIDARs platforms. LIDAR's been mounted to so many different platforms over the years. Each one of these platforms has its strengths and limitations, and you can just imagine where each one of those plays a role and how well it performs. But in this particular instance, we really want to talk about a UAV system that is Part 107 compliant, along with a survey grade accuracy LIDAR. And in this particular instance, we've got 2 cameras that are mounted on top of this airborne platform. Those 2 cameras are covering the 220-degree field of view that the LIDAR sensor is, and this starts to set up the discussion of how much information can we extract from a very low altitude. What you're seeing here is a breakdown of the various components that would be part of a survey grade UAV LIDAR. On the far left hand side, you're going to see a digital camera, the GNSS components in the middle along with the IMU sensor, and then of course a LIDAR sensor on the far right hand side. So with this particular slide, I wanted to show some examples of LIDAR miniaturization. You're seeing 2 different systems. They have a little bit of different weight and of course a little bit of different performance capability, but over the years LIDAR sensors have evolved to produce smaller, lighter, higher performing sensors to meet emerging requirements such as UAV. Okay, then here's some typical statistics that you'll find from a UAV system. We're 220-degree field of view, which means it's very effective at low altitudes. On this particular platform, there's a 30-minute flight time. This will, if you're covering a broad area, this will cover roughly 60 acres very effectively. Lewis previously showed a DJI platform, an extraordinary sensor or extraordinary airborne platform as well, with about a 15-minute flight time. So with a 30-minute flight time, we're able to grab about 4.5 gigs of LIDAR data, 14.2 gigs of image data. The LIDAR data then will transfer into about 1 gig of LAS files. So what you can see here is the rough size of the data. It's quite frankly not as enormous as many people felt it would be. And then in terms of processing time for a project like this, what we find is that it's a roughly 1-to-1 acquisition to processing of the point cloud. So if we're going to spend 30 minutes for data acquisition, we will spend an additional 30 minutes to process this to its conclusion. Okay. We're in the Part 107 world from the FAA, and I just want to emphasize this clearly. Each platform must be less than 55 pounds in weight, daylight, twilight operation, 400-foot max altitude, 87 knots max speed, Class G airspace only, external loads allowed, cameras, LIDAR, Amazon stuff. Pilot certification is required. You must certify the drone. You must perform pre-flight visual and operation checks. The UAS must be registered. You are responsible for compliance to all laws. You must keep an aircraft log, and you must report to the FAA any loss of at least $500. So we've covered those rules pretty effectively. Now let's get into action. So under the auspices of Michigan Department of Transportation and one of their great service providers, we conducted a highway bridge project survey with the UAV platform that you saw previously. So the image that you see is a comprised image of 2 different flights of roughly 30 minutes each to collect the point cloud, all integrated together, that you see below. The green squiggly lines that you see above that, that represents the trajectory of the Avalanche GNSS from the system. You can see that we took this at 2 different flight altitudes. So the strength of this platform was the ability to capture very precise data from the top down to see the entire intersection, and without missing data from an obscure line of sight that you might find in other platforms. So we're going to turn to the role of GNSS and the distribution of measurements. So here's that same Regal LIDAR UAV system with some stats on that particular project. And the video that you're seeing activated here is a 35-meter tree with 4.6 million points on it. And what this, the purpose of this video is to show the correct distribution of measurements and how this is critical for data fidelity and accurate processing in a timely manner. So you can get systems that have lots and lots of points that they pump out there, but if they're not correctly distributed and time tagged, you're going to be missing a great deal of information. All right, moving on to the next strategic area that I wanted to cover, seamless GNSS integrations and calibration. So first step, of course, is integrating the Regal LIDAR engine with the Applanix GNSS, and the precise time stamping is the basis for the synchronization. And this then allows us to bring other sensors into the mix. So Gigi vision systems, high-end consumer-grade cameras, thermals, industrials, FLIRs, things of that nature. Of course, we have software developed for system integration of these systems for kinematic LIDAR, and we also have software developed for calibration and calibration verification for this as well. All of that is very, very critical. So here we have an example of an airborne LIDAR system coupled with an RGB camera, a thermal camera integrated as well, and all of these systems calibrated together. So down below, we're seeing a point cloud. So this is a typical gray scale calibrated amplitude, and you can clearly see the image below. Here is the RGB image from the camera system that's perfectly oriented to the point cloud. And next is the thermal image overlaid upon all of this data, and of course calibrated correctly into this. This is not the RGB image. This is the point cloud, which has RGB information correctly attributed with color onto the point cloud. And in this particular thermal image, we've identified an area with rail cars that have a higher temperature than the ambient surroundings. We want to take a quick look and analyze this. And so we're able to do that in this video then is showing you a detailed look at the RGB information. And this allows us to get that element of information here, and then we switch to the thermal, and all of this then demonstrates the exceptional integration between the GNSS, the LIDAR, and the other sensors. So moving on, our next strategic area is the GNSS trajectory adjustment through RAI Precision. So in GPS denied areas typically found with mobile and UAV mapping, we can experience issues with GPS reception, and I'm sure the audience is very well familiar with this. So on the left-hand side with laser scanners, that system is going to be accurate to within millimeters. The overall system calibration in the middle from lever arms and orientation on through, they're very, very precise. And then we hit some GPS problems, and so we can be centimeters to meters off in terms of where it needs to truly be. So in the upper right-hand corner, you're seeing the original GNSS IMU trajectory, and then of course what we're doing is we're taking the taking all of this down to where what we're calling is truth. And so here is a better way to look at this. Here's a number of different passes, and what we find here is 70 centimeters of vertical separation, 50 centimeters of horizontal separation, and this is typical for what you might find with these GPS denied areas. So that was a detailed look, and I wanted to move on to a broader area. There we go. So we have here a picture coming from Rome, Italy. This is a mobile mapping project, and there's a couple passes that have gone through there, 3 different passes, and with those 3 different passes and GPS issues, what we'll find is that not every particular area comes in to the extent that we would like it to in terms of precision. And overall, we're roughly 60 centimeters out from all those different passes. So we turn to Rye Precision. And Rye Precision is an estimation engine. We begin with the initial trajectory coming from the GNSS and its particular accuracy. We rely upon some of the point cloud features and some of the correspondences of those features. In addition to that, we have the laser scanner accuracy to be able to give us some hints in terms of where we need to go and what we need to do. From time to time, we may even use external control objects, particularly if it's a very high accuracy Department of Transportation data collect, and then we create our smart trajectory model from all those elements. We of course determine a smart data handling process from this. We throw a couple of rigorous statistics along with a powerful algorithm into the process, and voila, we come up with our optimized trajectory, which creates for us the definite point cloud, or the truth, as we pointed out in a slide before. So in terms of height deviation that we saw in Rome, Italy, this is the 60 centimeters before Rye Precision, and through the magic of these powerful algorithms, voila, we have an accuracy of 1 centimeter. And then I wanted to show you also the detailed street lamp that we talked about earlier. So before Rye Precision, and then voila, after Rye Precision, we've cleaned that up and we're back to that 1 centimeter of precision that we need for the overall project. Okay, so we've covered all kinds of important aspects with regard to accuracy, precision, GNSS, things of that nature. So now what I want to do is put this all together. We have a UAV LIDAR data collect. This one took place in Indonesia. It's a pipeline project. It's going through very dense jungle. So in the upper left-hand corner, you can see a colorized point cloud and that fabulous jungle. And then in the upper right-hand corner, you're going to see some of those waveform returns that Lewis was talking about in his talk. So what we're able to do is to identify all those returns and remove them. And what that allows us to do is to capture the lower left image, which demonstrate that those the last returns from the LIDAR system and the vegetation perfectly identified and perfectly removed. And then we create a DTM. From this DTM, then, the contractor needs accurate contours for planning and construction. He doesn't need all kinds of point clouds. He just needs the information he needs for the project. So the lower right-hand corner shows the contour lines, which is the information that the contractor needs. This imagery, of course, is courtesy of GPS Land in Indonesia. I do want to thank them for their contribution to our talk today. So all of this demonstrates perfectly the effective integration between the GNSS and LIDAR. This sets the stage for data accuracy, processing speed, accurate and fast information that's expected in our world, and this takes us from big data to information. So General, I hope I've, at least in a small way, convinced you that we're a little bit closer to the dream that everyone's looking for UAV-borne LIDAR.
Okay, Lori, is this thing being recorded? I may want to admit that I may have been wrong in my initial thing, but I'm sure we can edit that out of the production. So
absolutely.
There you go. I almost said it. Okay. All right. Next, we're going to hear from a genuine expert and a real user out there. Pierre Champagner has worked for over 10 years in the bush as a geologist on mineral exploration projects, mostly in Africa. He figured there had to be a better way than using paper and Garmin maps to sketch out where rocks were, so he familiarized himself with UAVs. He's now mapping rocks like a demon using YellowScan LIDAR. At YellowScan, Pierre works LIDAR processing, training for end users, and after-sale services. So over to you, Pierre.
Thank you for that introduction, General Puss, and hi to everyone out there. Okay, now that we've actually covered the theory, I just wanted to give the audience a bit of an overview of how it all comes together in the field. So for this last sort of section of the webinar, we'll be looking at the benefits of direct georeferencing, DG, for simultaneous LIDAR photogrammetry system versus traditional aerial triangulation systems. First, just let me just introduce a little bit the company, YellowScan. Since 2014, YellowScan's been actually providing turnkey LIDAR for UAV to dozens of surveyors like you all around the world. Our team is comprised with experts with more than 12 years of aerial survey experience together with geomatics applied research. Basically, our innovative solutions are designed for surveyors by surveyors. LIDAR solutions are ultra lightweight instruments, the most accurate in that category, robust, reliable, and easy to use when you're in the field. One of the main question for US operation is all about Part 107 compliancy, as we've been debating. Well, our LIDAR system can be as light as 2.2 pounds, so that actually leaves you a fair bit of room to look at the UAV part of the equation, if you like. And when we spec out 2.2 pounds, that indeed includes the scanner, the GNSS inertial system, the onboard computer, and the battery. In short, everything you need to actually go out and survey an area. The YellowScan Surveyor, just displayed here to the bottom right, is armed with the APX-15 from Applanix that Lewis showed earlier on one of his slides. It can't really go lighter than that with this consistent quality and reliability. So basically, just want to push the argument a little bit further. We've got good news for you, General Poss. First is that the YellowScan system can easily fit Part 107. Actually, in France, the regulation is even more restrictive in terms of UAV payload limits in certain urban scenarios. So the restriction in France is about 17 pounds. And well, guess what? We still go out there and fly and scan areas. The second is that we actually already have clients out there flying YellowScan systems successfully and acquiring data. So the thing is sort of being pushed into a bit of a routine now on UAV platforms. If you want the point cloud to be colorized, not a problem. A camera, we can fit a camera, sync it to the LiDAR unit, and record positional and angular values for each triggering event. This will make DG photogrammetry possible. And what more direct than actually seeing your point cloud displaying live as you fly? This is now actually possible with our live station software, which an overview is sort of given on the slide here. The application that we've been dealing with so far are quite various. Some of the main ones are highlighted on this slide, and as you can tell, our core application looks at discretizing power lines, like Lewis was mentioning, something you can't actually do with photogrammetry. Mapping terrain covered with trees, unveiling structures or fine topographical lineament features underneath vegetated area. Basically, any application for which photogrammetry reaches its limit. But there's more to LiDAR than just its ability to actually penetrate vegetation, and this is what we'll look at in this presentation. The following sort of comparison experiment that we did in France was done on a 25-hectare quarry southeast of France, directly west of Monte Carlo, as you can see on the map. It's a quarry site that produces sand, gravel, construction material in general. As in other quarries, the operator needs, like what you refer to in the military application, a common operational picture, and this on a sort of monthly basis or quarterly basis. This will generate progress report, volume calculation. The operator will actually be able to plan infrastructure on that, and other sort of derived product from these base maps. On the same day and under the same conditions, we had 3 surveying techniques deployed by various contractors. This included a terrestrial LiDAR scanner, a DJI Inspire, and a YellowScan Surveyor mounted in dual mode with an RGB camera, actually a Sony Alpha 6000 if you want the details. The aim was actually to compare the deliverables in terms of quality, but also to look at the operational constraints and timing. All techniques, in terms of operational consideration, all techniques required initial survey setup. Before starting a survey, the terrestrial LiDAR scanner requires a fair amount of work to actually establish control points for each site. The aerial triangulation, on the other side, relies on visual target control points that actually need to be laid out before you fly the survey, and then needs to be picked up with a differential GPS, for example. The YellowScan system setup requires a base station set up on a landmark to actually enable the PPK process later. Otherwise, sometimes mine sites run their own base stations, so you can actually use that information and just start flying your drone whenever you come to the site. So there's, even for the YellowScan setup, there's almost no need to do some pre-checks on the terrain. The survey process is far from autonomous with the terrestrial LiDAR system. It involves a lot of manual actions, to scan stations after stations, and so on. For the UAV platform, it's quite handy and autonomous. The only difference between the sort of DJI platform and the YellowScan platform is that you need to, for the DJI platform, you have a flat flight plan. For the YellowScan system, you need to do some adaptive terrain flight plans. In terms of timing now, and how it all compares, the table actually specifies the amount of time that was spent in the field, how much time was spent doing manual processing. I mean button clicking, basically human intervention, and how much time was required in terms of machine computing. You see that 6 hours of terrestrial LiDAR scanner surveying covered about 1 hectare at a GSD of 1 centimeter, while the LiDAR managed to cover 25 hectares in 2 hours to produce a point cloud at a GSD of 5 centimeter. The two products that you see on the photogrammetry column were generated from aerial triangulation process. The colorized point cloud was done with the 16 megapixel of the default camera on the DJI Inspire, and the other colorized point cloud, 24 megapixel, was produced from the Sony that was fitted on the LiDAR, the combo LiDAR configuration. As the table shows, the processing time of both of these resolutions are quite different. The aerial triangulation process is quite hungry in terms of time. The takeaway from this slide is basically the productivity figures indicated with an arrow there. The LiDAR survey and processing is fast, and when combined with direct georeference photogrammetry, your colorized point cloud is only sort of minutes away. In terms of accuracy now, and what sort of accuracy you can achieve with those systems, 7 target points were used and pre-installed for the photogrammetric aerial triangulation process. These were used as control point for the photogrammetry products. The LiDAR only required 1 landmark to actually set the base station on. An additional 27 ground truth points were picked up the day of the survey as validation point, true validation point. The box plot that you can see on the slide shows the dispersion of the vertical shift between the different product and produced point cloud product and the validation points. So all that explains the difference in Z. Looking at RMSE Z values, the LiDAR does a better job by about 15 mil compared to the photogrammetry aerial triangulation technique used. That's 1 point, but that's point by point, comparing only point basically. If you look at larger area, so like patches of point, and we could do that because we had the TLS to actually validate a bigger area. Now, if you compare that, like for example, that 10 by 10 meter patch, which actually included a sort of a sharp slope changes, things look quite a little bit different. We extracted the TLS data over this patch and used it as a reference point cloud. we extracted the exact same patch for the other data set and computed comparative statistics. The high-resolution photogrammetry product seems to be providing a reliable picture of the patch, so does the LIDAR point cloud. The 16-megapixel camera actually nicely illustrate the typical sort of trapping effect of photogrammetry point clouds of a sort of extruded object generating sharp slope changes. So the actual error on the 16-megapixel product is about 15 centimeters basically, while the LIDAR produces a product like under 5 centimeter accurate, looking at, again, a patch of ground instead of just point by point comparing. Now, in a more sort of qualitative manner, this snapshot sort of reiterates Lewis' presentation when using LIDAR in vegetated area. This is a portion of the mine site where you actually could pick up a few trees, and we're just looking at snapshot presenting the same sections between the photogrammetry and the LIDAR point cloud. Underlying ground changes can be sort of confidently mapped, and trees profiles are quite described in a better way and a more reliable way with the LIDAR dataset. In terms of infrastructure now, the snapshots are just comparing the two data sets in terms of photogrammetry and the LIDAR data sets, and these images are quite self-explanatory. All objects seems to be sort of covered in a sheet, while the LIDAR data set reveals their true geometry. Fine conveyor structures, as you can see on the images, they can be clearly described with the LIDAR, but they're almost sort of missed on the 16 megapixel data set. Now, in terms of another sort of last comparison snapshots on sort of sharp slope changes, you can see the three products that we were talking about, the two photogrammetric product and the LIDAR product. In the center, you can see the 16 megapixel photogrammetric product, and you can still, on the profile section underneath, you can still see the sort of typical wavy profile of this sort of data set with this kind of resolution. 24 megapixel camera point cloud appears to actually nicely pick up the sharp slope changes generated by this was actually a bulk bag storage, but the actual edges of the bulk bags are picked up quite nicely. But there's still going to get some light conditions that will affect the product, generating gaps of information. So as you can see on the left-hand image, you have all sorts of dark patches that are actually no data areas, while on the right-hand side, the LIDAR point cloud captures everything because LIDAR is an active process, so you don't actually need light from the sun to actually generate results. So that's one good point for the LIDAR. And to actually conclude a little bit this presentation and to give you the key sort of features, we've seen how tedious the terrestrial technique was to install and use. We've seen how important the size of the photogrammetric sensor was in parallel with the processing time required during the aerial triangulation process. Whatever the size of the camera, you'll always run into some light condition issues that we've actually picked up on a few areas in that query site. The LIDAR, on the other hand, is quick to deploy, quick to produce accurate point cloud, and actually is a reliable tool that you can fit on a lot of different platforms. And just to sort of sum up a little bit more on the benefits of simultaneous acquisition versus aerial triangulation photogrammetry, well, basically you'll get faster survey time and faster processing time with combo systems, but also all the benefits of remote sensing survey, which includes all the sort of safety aspect of remote sensing surveys. But also, not only are you getting this, but you're also getting all the benefits of doing a LIDAR survey. So that's all the advantages of having an active light, which will actually be able to capture even homogeneous surfaces like snow or sand, featureless materials that will be hard to pick up with photogrammetry. You'll also, and Lewis pointed that one out, it's actually the only tool at the moment that will capture fine infrastructure like power lines or other sort of conveyor structures. Just wanted to finish up with a few invitations. We're running an international user conference in France, south of France actually, next to Montpellier on the 29th and 30th of June. So if you want to know more about the YellowScan solutions and to actually see them live, just come and visit us on the website and you can even register. So there you go. Back to you, General Poss.
Okay, merci beaucoup. All right, I'm going from possibly wrong to shot down in flames, and you can record that. So I guess you can use small UAS for LIDAR. I was wrong. Okay. If you want to get copies of the presentation, we'll have those posted up online at that address put on there. These are our actual email addresses, so if you want to send emails to anybody in the panel, there you go. All right, and we're going to do some questions, but first, I think we've got our last poll. Am I correct, Lori?
That we do. And final poll here is, are you ready to invest in LIDAR? So where are you at with this question? Right now, tech is mature, within a year, 1 to 3 years from now, or maybe beyond 3 years. Looking like 26% saying right now, 32% within a year, 30% 1 to 3 years from now, and 13% beyond 3. So, General Poss, any thoughts there?
That's kind of interesting. I was reading from the other polls that folks really thought this was ready to go now, but that's kind of interesting that we've got 43% think it's not going to be ready for over a year and even beyond 3 years. I did not think that from the other polling. Okay, well, thanks for that, Lori. And I guess we've got a few minutes left for some questions here, and we got some really great questions from folks. But the first one I want to ask, and if I could ask each of our 3 panelists, and we'll go in the order of Jim, Pierre, and Lewis, could you give me your perspective on what you think are the big markets for LIDAR, UAS-based LIDAR these days? Where does this really make sense in today's economy?
Thank you, General. The current LIDAR markets that are established, mature, that are looking for utilization of UAV solutions are well known to many, many people. You have power line mapping that people want to look at. Right now, power line mapping utilizes helicopters, and there's a cost and safety aspect to that, and so they're looking for UAVs to be able to provide that. For transportation infrastructure, people are looking for solutions for those as well. But also, I want to go back to the land surveying companies. All of these land surveying companies have projects that are probably more development oriented, and they need to come up with better solutions for their customers, and the UAS solutions are right along those lines, and that's where the application is going to be ramping up quite a bit rapidly.
Cool. Pierre, what's your perspective?
Well, I think because of the flexibility of the UAV to actually deploy, and the fact that it's quick and easy to deploy, I don't think it will replace any sort of fixed wings or helicopter, but it will go, and it will come as a complementary solution, and so you'll have a sort of a big need for LIDAR data sets on utility mapping, probably civil engineering, and on the forestry side. So basically any sort of applications that will run into the photogrammetry limitations that we've been talking about before.
All right, sounds good. Lewis?
Thank you. Yeah, I would say that you have to look at the cost effectiveness of UAV versus manned aircraft. And so we've done about 500 projects in the last couple of years, all structure from motion over mine sites. The sweet spot is 250 acres or below are effective for UAV mapping. And we always get into this situation where the mining operation wants to do overburden removal. That's where they still have trees, vegetation, and they want to do the computations for that because they often contract it out. That's a job that is best done with LIDAR. So I really think in those kinds of applications, it's a perfect fit for LIDAR, and there's probably enough of it to amateurize the cost over a reasonable period of time.
Okay, that's great. Okay, Lewis, I'm going to keep you on the stage here. We got a question. Could you go a little bit more into detail about where you see UAS as being price competitive to other types of mapping, aircraft, ground-based, vehicle-based, and all that? You mentioned 250 acres is one stopping point for LIDAR. Are there any other areas where you have issues justifying the cost of small UAS LIDAR?
Well, I think that, we're not really inventing any new mapping operations that I'm aware of. So it's a replacement technology. I'm replacing a guy climbing a cell phone tower, or I'm replacing a pogo-bound surveyor on the ground. So it's really a matter of is a LIDAR on a UAV going to be a more cost-effective solution? So again, I think on these high payoff environments such as mine sites, it's a dangerous environment. I need to get in and get out, do it quickly. Certainly tower inspections where you really, what price do you put on safety, and these kinds of niche applications, they're well designed for LIDAR on a UAV. The big problem that we have is that the technology is moving so rapidly that we really need to amateurize that cost over 24 months or less when we think about investing in this technology, at least in my opinion.
All right, great answer. Okay, Jim, this next one's for you. We're getting quite a few questions about power, and I know we've covered weight and mass pretty well, but could you give us some idea how much power these systems are going to pull?
The modern LIDAR systems are all being powered from the battery supplies that are on board the UAV platform. So you saw two examples, or three different examples. The DJI example has enough power to be able to support LIDAR, a simple camera, and the platform itself for roughly 15 minutes. The Regal solution was a little bit larger. It's about a 30-minute power supply, so there's quite a few more batteries that are on board. And Pierre, what do you find? What do you find with the YellowScan platforms that you're flying?
Well, the YellowScan systems are quite lighter than those. They're actually minier than the Mini, if you like. You can fit them on a lot of different platforms. What we've seen is the typical flight time of like 15 minutes for the sort of multi-rotors, typical multi-rotor, but we can fly them on larger platform that will fly for about 40 minutes or an hour. So all depends on what sort of platform you actually put them on. It doesn't, because it's so light, it doesn't need that much power to actually just lift it. It's fairly versatile, actually.
So, General, I think the ultimate answer to that is platform dependent. There's a couple of fixed wing solutions that are out there that are generating power as they fly. There's some fun experimental systems that are bringing in solar energy as they fly. So there's more to come. The batteries are getting more efficient, and I think we'll be seeing longer flight times shortly.
Great answer. Okay. All right, I'm going to take this next one. We've got a question about is there any ongoing research within the Air Force or DOD to develop LIDAR systems on UAVs, specifically small UAS. You know, I got to tell you, the Air Force runs between tepid and cold on LIDAR, and it's not that they don't believe in the technology. It's just they think someone else ought to pay for it. The Air Force, for the past 10 years or so, has been very resistant to take on any more national missions because national missions eat up about 30% of our budget, you know, from supporting NASA in space to, you know, supporting NOAA, flying in hurricanes and whatnot. And the Air Force's view is that mapping is a responsibility of the National Geospatial Agency, and they should do it. That said, during Afghanistan, we flew quite a few LIDARs out there on a variety of platforms, and we've only just demodded our last one, the alert system. They did fantastic work. They were flown by the Air Force. They were generally paid for out of contingency funds, so they were sort of free for us. The Air Force has put some effort into developing a podded LIDAR system. Air Force Research Lab is working it to put on the MQ-9 Reaper. The United States Army has never lost its interest in mapping and has never trusted the National Geospatial Agency to provide it quality mapping products. And as a result has fully funded with Army funding the Buckeye system, which flies in a King Air twin-engine turboprop aircraft and provides a medium altitude LIDAR. Matter of fact, they're just going through a major upgrade product there. So, okay, so that's enough from me. Okay, Louis, I'm going to pick on you, and I'm not sure if you're not the right guy, somebody else can jump in. There's been some questions about the other side of LIDAR in studying, you know, atmospheric phenomenon, detecting chemicals and all that. Is that something you're comfortable in talking about?
Well, my wife says I'll talk about anything even if I don't know anything about it, so sure. Yeah, I think, you know, that was really the genesis of LIDAR, I think, and with atmospheric studies. It's done a lot today, even from space. So NASA flies a couple of space-borne atmospheric research lasers. I know the company Optec, which is very close to Planix, geographically has done a lot of work with land-based LIDAR that is pointed upward for atmospheric studies as well. So it's not something that my own company deals with, but it's still a very active area of research and development on the laser side.
Okay, thank you. All right, Jim, this next one's for you. You know, we've kind of talked about the you know, the investment and performance aspects of LIDAR systems. So what else do you have to really think about before you run out to Amazon and buy a LIDAR system? What are other considerations?
So a little earlier we talked about investment costs for the technology. There's many other aspects that need to be taken into account. Generally, you pointed out early on the size, nature of the data. So you have to have computer systems to be able to process this in an effective manner. In addition to that, as Louis knows as well as anyone, third-party software processing is critical to all of this. Every different software has a tendency to have tools that are critical for one aspect or another, so software becomes an important aspect. And then, of course, your network system to be able to house the data, whether you're going to store it, what sort of policies or strategies you're going to utilize with regard to things that are found on the web. Amazon has some great servers up in the cloud that will be able to store data, and you can access either derived products from the LIDAR systems or the camera systems or imagery, things of that nature. So it goes a little bit beyond the cost of just purchasing the technology.
All right, great answer. And I'm looking at the clock, and it looks like, Lori, I think we're out of time for questions. So fantastic. I learned a lot in this seminar, and I thought I had known everything. And I really particularly want to thank the panelists for explaining lasers without using the term laser and making the little bunny rabbit things like they did on Austin Power. So great. Lori, I'm going to turn it back over to you for wrap up.
All right. Thank you so much, General Poss. And before we'd like to sign off, I'd like to thank each of you for joining us and certainly trust that you found today to be of value. Special thanks to our distinguished panel members and, of course, our sponsor, Planex, our co-hosts, InsideGNSS and Inside Unmanned Systems. And most importantly, thanks again for joining. This is Lori Dearman saying, hope we see you on the next one. Bye for now.